Great. So thank you all for joining, and thank you for being a part of this workshop where we'll be going over Julia for engineers with a focus on algorithms, component-based modeling, and many of the modeling toolkit workflows. I'm excited to present this to you. I want this to be an interactive session, so I'll keep my eyes on the chat, and we can answer questions as they come, both via Q&A and the webinar chat. Because it's an interactive session and I'll be doing interactive coding, it's often great if folks have questions at the time that they ask it, and if I see it, I'll try to address it. I may not address all questions as they come in. Some will hold till the end, but I think this should be a great session, and hopefully everybody will learn something today. So without further ado, let's dive in. We're going to be doing this on JuliaHub. And you can navigate to JuliaHub, sign in, and you get some access to 20 hours of free compute a month. And we'll be doing this using a notebook. So once you've logged in to JuliaHub, you can go to your notebooks view and just search for webinar is an easy way to do that. You will find my public webinar here. It's going to be pretty bare bones at the beginning because I want to incrementally develop this with you all. So that way you can kind of see what's happening and understand what I'm writing instead of just, seeing the final solution pasted. You'll understand a little bit of why I'm doing what I'm doing, and hopefully that will be informative to everybody. So you can get that started. It takes, if you've never used a JuliaHub notebook before, especially because we're going to be loading modeling toolkit, differential equations, plots, all of these very large packages, it will take a few minutes to precompile all of those. These are precompile files that end up being saved once you have loaded it once in one time. But this is the file, and you can click edit this notebook to access an interactive session for you to work with as we go through it all. So that's going to be our place where we're going to work through this. If you don't get it running, that's fine. I'll have the final version here uploaded to JuliaHub in exactly the same spot, so that way you can always come back to the final version as it was, and this recording will also be made available afterwards to all participants, so that way you can go back and see any magic that I did and figure out what actually is going on. So without further ado, let's dig in. We will kind of look at what modeling and simulation looks like in Modeling Toolkit. We're going to be using the Pluto environment, which allows us to look at some visuals, plots, as well as the text of the session here will appear. The main learning objective is to introduce you to Modeling Toolkit, and as we do so, you'll learn a little bit of Julia. But the idea is we want to focus on the modeling first, and along the way we'll pick up Julia as we need it. So even if you've never used Julia before, you're in good hands. We won't, there'll be some magic that I'll wave my hands around, but hopefully you'll be able to understand everything that I do here. I try to make it understandable in ways that anyone coming from a modeling or engineering background should be able to understand. Just a brief overview about the language itself. We are firm believers. I've been a part of the Julia community for over 10 years now. It's a very awesome language, a very awesome community, and really the 1-2 punch that so many people come back to over and over again is that it is fast and easy to use. But bringing both performance and ease of use together is really fundamental to why folks use Julia, and really the reason why Modeling Toolkit has become such a powerful way to do industrial modeling and all sorts of applications. And that's where the mathematical capabilities really shine. And because it is a fast language, it means that all of these functionalities are written in Julia itself. It's a unified language. It allows you to really understand what's happening, and that's built up an entire vibrant ecosystem. So why might you use Julia? Well, one answer is that expressive, right? What does that look like? Well, in a Pluto notebook, actually, we can write LaTeX directly and, grab some algorithm from a textbook or, some, standard that we want to model, and we can write it in as LaTeX, right? This is just the pure maths view of this. Julia doesn't understand anything that's going on here. It's just a visual representation where we have three state variables, S, I, and R, and we say how they change. So thanks to the global epidemic 4 years ago, we all became epidemiologists of some sort. This is the very, very basic epidemiology model where you have susceptible people, infected people, and recovered people. People become, leave the susceptible population once they become infected. They move in. So you see these two terms here are balanced. You have the negative here and the positive here, because the susceptible become infected, and then at some point they recover. And there are two rate variables here, or parameters, that govern how quickly each of these things happen. Beta is the infectivity, and gamma is how long it takes to recover. And so this is a standard SIR textbook model, but that's all it is, right? It's just the maths equations. It's not telling Julia how to do it. It's not saying how to model it. So how do you do that? The implementation of it looks very similar to the actual model itself. So we're going to bring in modeling toolkit. We say that we're going to use time without units and a differential operator without units. That's kind of the magic of this line here, is saying, let's grab the standard time and the standard differential operator. Let's define what our three variables are, what those three populations are, and what our two parameters are. And we can write this in Julia. You can just use beta and gamma directly using tab completion. So beta is \beta, just like you would write in LaTeX, and then hit tab, and a tab completes. So that's how you write these things. And then we put them together into a system of equations where the differential of S is defined exactly how we have it written there. The DI is, again, exactly how it's written there. And hopefully you can see, right, these three lines are exactly that textbook algorithm. There's a few lines of extras going on here, but you'll see that this is very similar. Yeah, the notebook on the public JuliaHub is slightly different. I'm using a separate runner here. What will end up, sorry, for context for others, there's a question in the chat asking, that the version of the notebook looks slightly different. I had rearranged a few things just in the few minutes before here, hopefully to make it a little bit easier for you all to get started on JuliaHub. The version that I have running right now already has everything loaded, so it looks just slightly different, just so that way I don't need to wait for those packages to load, and hopefully while I talk, the packages load for you all. So that's the reason why. Yeah, thanks for the question, and sorry, I should have made sure that those two things were in line. But you can see here, this is our model and the implementation, and then we can look at what happens, right? So what does this model look like? And look at that. It spits out exactly the same LaTeX. It looks almost like we did no work here, right? It happens to print out almost exactly the same. I guess it rearranged the parameters to appear after the variables. Otherwise, it's exactly the same. Oh yeah, and this term appears here, right? It just kind of depends upon how it wants to arrange the maths, but that's exactly equivalent. And you can really easily check to see, does this model match what is going on in the textbook? Like, did I do this correctly? And it's a really nice way of evaluating this. So what do we do when we solve it? Well, you can say, let's plot a solution. You wrap it into an ODE problem. And the things that I'm putting in here are the initial values of our three populations. So again, they're in order of that I defined them, SIR. So if I have a population of 10,000 people, 50 of whom are infected, nobody's recovered yet, and we want to say 20 days, right? We didn't put units on this. This is all just kind of theoretical, but you can see how the three populations evolve over time. And then these are our two parameters, the infectivity and the recovery rates. And you can see what happens if I change these things, right? If I just decrease the infectivity a little bit, it flattens that curve. So this is the promise of Julia and Modeling Toolkit. And what we want to do here is we want to end up seeing, what happens, or how do we do this, and how do we take what we have here from a very simple toy example and extend it out into a larger system that is maybe more representative of a real engineering workflow. So from the basic differential equations to a real modeling equation. I'll pause here. It seems like there are a few questions of how to find this notebook and where to go as you get there. Really, a lot of what I'm going to be doing here is going to be starting from scratch from this point forward. And so you can use any implementation you would want, but if you want to start from the starting point I put on JuliaHub, that's at JuliaHub.com. In fact, if I go to JuliaHub.com without logging in, you'll land at our general landing page, and you want to just click the start for free log in however you most like to log in, either email registration or any of the open authentication options. We just use your email to figure out how to associate the account with you, and then you can go in and go to the notebook section on the left here. And by clicking in this particular search bar here for the search of notebooks for webinar, you'll find I have a public folder here with today's date and the modeling webinar. That's how you can access this, but it will take a few minutes if you've never done this before to pre-compile all those packages. All right, so we're going to use a bunch of packages in the Julia ecosystem. Most notably, we're going to be leaning a lot on the SciML ecosystem. And so what we're going to be doing is we want to build and develop a model that's a very simple model, just a spring and a damper, where we take some force and apply it to the spring, either pull it or push it, right? You want to see where the spring ends up finding its equilibrium. And now in this case, in a real physical model sort of thing, our differential equations look different, right? We have our spring component, which is just the displacement of the spring times a spring constant. We have a damper component here that's represented by this aspect of the cartoon that has some damper parameter that just restricts how quickly things can change. So that's the x dots, or the velocity, and those things must equal the force, right? These must be equal. And so this looks very different from the kind of algebra of a differential equation, right? This is a more real world physical modeling task where all we have are forces and our state equations. So how can we build on this to create a model or a system that can simulate it, just like what we did with the epidemiology example, right? And so the first thing that you might think is like, well, how do I find a differential equation for this, right? Like if we're going to be standing atop of modeling toolkit and differential equations, what is this, right? Like what do I do with this equation? F equals, the displacement with these things. Well, we can kind of start off by just defining our constants, right? We know that D is a parameter. We know that K is a parameter. We have some spring force. We know that we're going to apply some force F. And of course, you could think of these as having units or doing this a little bit more carefully. But then we want to see how the system evolves over time, right? And so we're going to look at some time steps. So we have a delta. Let's use a delta, delta, capital delta T as our time step. Just do a bunch of steps over time and kind of see what happens to the system as we apply this force to the spring damper system. And let's give ourselves a tolerance, right? You might want to solve this to some tolerance of how accurate does that X need to be. And this is a fine way to do this. Actually, if I try to execute this, Pluto will complain. It'll say, hey, there's a bunch of expressions here in this one cell. Do you want to fix it? And what I want to do actually is, because we're going to model this in two separate ways, I want to be a little careful about how I do this, because Pluto is an interactive, reactive environment that really likes to only have one definition available at any given time for a variable that you set in the system like this, or these are all parameters of their system. So instead of defining them, let's gather them all together into a data type that will kind of keep them together. So this is going to be our data type, and we'll call it P, like this. And so this gives me a collection of all of these things here. So we have, and you can just see, right, that's just doing gathering it all together, and I can look in and see, like, so P dot D is our damping coefficient. That's going to be 1. P dot K is our spring constant. That's 1,000. All of these things are here. So this is just a little bit of organization, nothing more. But in terms of what the Julia is, this is defining a name, and we're calling it P, that contains name value pairs. And so the name of each one of these values has a name to it, and you can kind of see how that works as you go through. So now what? That's the easy part, right? We have our constants. What do we do next? Well, one way that you might think about trying to solve this differential equation is just by writing a function. And in Julia, we can do that with the function keyword, f. And what we want to see is how the dynamics of the system, right? And so each time point is dependent upon where it was the previous time step. So we have f of x, which is going to be our current time, or x, maybe let's call it x sub t, to be our current time, and x sub t minus, oops, x sub t. Can't I do that? How do I get the -1? Well, t, or let's just call it prev, x underscore p, like that. So at our given time point, we'll have x of t. At our previous time point, we'll call it x sub p. And what we want to do now is implement this force equation, right? So how do we do that? Well, we know what x dot is, right? If we have the previous time point, we're going to take steps at 10 times to the -3. So those are going to be our time point steps, and we know exactly how much this has changed. So we can just see what x dot is, right? So x dot, you can also implement this in Julia as a nice little way of representing our derivative of x, is just going to be, well, the difference between x at our current time point minus x at our previous time point divided by our p dot delta t. right? So that's going to give us our finite differences. It's a really naive way of doing this, but that's okay. This is just kind of learning a little bit of Julia, of how we define functions and work with things. We'll move on relatively quickly here. So this is our derivative of x, right? Our position x. And then we have two sides of our equation that we want to balance, right? So we have our left-hand side of the equation is going to be our parameters, the damper constant times x dot, plus our spring constant times x. And that's going to be our x at our current time point. And then our right-hand side, well, that's just simply going to be our constant force that we're applying to the system. And we want to know what how far away are we from having a good answer here, right? And the easy way to do that is just solve for 0 and return the left-hand side minus the right-hand side. And so if we have a good time point here, then we're going to get an answer of 0. And that's what we want. We want to find an answer of 0. So let's solve this for 10 time steps. Very simple. We want 0's 10. Give us an array of 10 time points. We'll just start at 0, start with a 0 displacement of our spring and watch how the system evolves, right? So how do we see what the first time point is? Well, it's our x's of 1. Well, no, we want to compare our current time point based upon the previous one, right? So we have two values here. We have our value at our second time point and our value at our first time point, and we just want to see, how far off are we in our force? Well, if we didn't move, if our spring didn't move, our forces aren't balanced. So we need to change what x's of 2 is, right? We need to change what our second point is in order to solve this, right? So 0.0 is not a good solution. You can start moving a little bit. So 0.1, oh, that went too far, right? So 0.0, my forces were negative. 0.1, my forces were positive. What about 0.01, right? You can kind of see, oh, that's negative 80, 0.02, negative 60, and kind of work your way through here and do a check and guess to see how are we? Okay, so that's our second answer, right? This is our second time point of our solution. So we could say x's of 2 is 0.05. Great. Now we just need to redo this 8 more times, and then we get our solution. Of course, that's not a great way of doing this, and there are much better ways of doing it. One slightly better, but still not ideal way of doing this is just with a for loop, right? We could do a for loop where we go from I as our second value to the 10th value, and we want to figure out, we want to minimize the evaluation of f at every time point, right? So do exactly what I did by hand, by check and guess, but we want to do it automatically. And an easy way to do that automatically is with gradient descent. So we can implement a very basic gradient descent algorithm here, where we could start with, we're going to now look at the derivative, not of x, like the position, not the derivative of the spring position, but rather the derivative of our guess at what the next time point of that spring position is going to be, right? It's a slightly different way. So it's not with respect to time, but it's with respect to the system at large. And so we can start with maybe a delta x as, say an nth, and just say, hey, while our delta x is greater than our, remember we had defined that tolerance of how accurate we wanted this to be. While we're greater than our tolerance, we want this to be the absolute value, right? We want to optimize it, right? So how do we change what our current guess is? So we have, x of I is our current value. So we have x's of 2, right, is going to be, that's accurate. We already found that one to have our force is balanced, but how do we balance all the others, right? Well, one way of doing that is by updating our derivative, so that delta x is going to be, well, we evaluate x's of I, x's of I minus 1, right? We want to see how that compared. And then we want to divide it by the gradient, or the direction, like which way should we step, right? How far should we step and stuff. And this is just very simple, straightforward gradient descent. One way to do that that's kind of fun and cute in the Julia ecosystem is using a package called forward diff, where you can just ask for a derivative of any function, derivative. And what we want to do here is, given a value x, we want to see what that evaluation of f of x at the previous time point is. And in this case, it's going to be x's of I minus 1. And we're going to pass in x's of I like that. So this is a little bit funny, and this is a complicated line of code here. But what's happening is I'm saying I don't want to pass both my previous time step and my current time step into derivative, because I want to take my derivative with respect to the time point that I'm optimizing, right? And so this is a little bit tricky. So I create this is an anonymous function that just compares our current value of x's against the previous time point and holds that previous time point constant. So by putting it as inside this function and not as an argument, it's a constant. And then we take the derivative with respect to the one argument we pass, which is our current position at our current time. So that gives us our derivative. And then we can update our x's of I to be, some minus our delta x, right? And so this will just keep going over and over and over again, updating our i's until we hit our tolerance. I can execute this, and hopefully we'll end up with an array that is optimized. And sure enough, that looks something reasonable. And of course, I can plot that. And we get something like this. And so this is just pulling on a spring with a constant force. You just stretch that spring and get to some equilibrium, and it's damped. And then we could go back and change these parameters and have all sorts of fun with that. But let's look at a better way of doing this. This just kind of, what's your appetite of using Julia? Just to kind of recap some of the interesting bits of Julia that we've looked in during this point. We looked at a for loop here, right? Control flow, very straightforward. You can do I equals or I in 2 to 10 like that. Both are equivalent. We started with some value, and then here's a while loop, right? So we're just asking, while this, our tolerance is greater than what we wanted, we're just going to update it. And the way we update it is by using one of the built-in auto differentiation mechanisms in Julia, or package-based auto differentiation mechanisms using forward diff. And then we updated it, we got our x's, and we plotted it. We have our 10 time points. Of course, we do a lot more with the labels and things, but I don't want to spend too much time on this. This is just a very simple example of getting our hands wet working with this model. Let's do this better. So one way that we can do this better is through component-based modeling. If you remember, we had a little bit of a tricky time thinking through how we think about the mixture of the force, the spring constant, and the damper. And if you think closely, we are missing some parts of the system, right? We didn't really talk about how our spring is attached to a ground point, or where that force gets applied. We left out some big things, and we kind of played a game with our x here as being the displacement of the spring. And we're starting at a neutral point. What happens if you start somewhere else? How do you extend this to more complicated systems? And let's start building up a system using a spring damper to think about how you do this in a real world situation. And a really common spring damper system that everybody knows about is the suspension on a car. right? You have a wheel on the ground, and there is explicitly, if you look under your car, you can see the spring, you can see the damper, those are your shocks. And it's a really great system that, keeps you from shaking about every time you hit a bump in the road. So let's do that. And the interesting part there is that there's not just one spring damper system. There's the spring damper system of the actual suspension. The tire itself is rubber and can kind of be modeled as a spring damper system itself. The seat that the driver sits in also has some springs in it, also has some dampers in it, and can also be modeled as a spring damper system. So how would we start building a more complicated example? And the toy that I started with here, boy, that would be hard, right? If you wanted to write out all those equations, even if you didn't do the integrations by hand, and used a package to do those integrations, goodness, that would take a lot to make sure that you have all those things correct. When each component is really, it knows its entire universe, right? The spring, all it cares about is where it's connected. It's two points here. Where does that connect, and how taut or stretched is that spring, right? And how far away is it from its neutral position? Same thing with the damper, right? It just cares about the two points here, and instead of the position, it's how quickly, what the velocity of those two relative points are. And if you're running this on top of a road, well, what you care about is not that the road is always constant, but you want to look at what happens when there's a bump in the road, and then how does your system respond? So let's start building this together in a component-based modeling using Modeling Toolkit in a way that is reusable, extensible, and inherently buildable. You can build more complicated systems, and that's really the magic of Modeling Toolkit's component-based modeling, is that it's all components. Everything is a component, and each component can be modeled independently or connected in interesting ways. So let's begin. And to begin, what we want to do is, well, let's start with a spring. And there's a macro in Modeling Toolkit called component. And we've already seen a few macros. Macros in the Julia language are these special @ things. And I actually used it up here when we were doing our Julia implementation to do a few things within Modeling Toolkit, right? We defined our variables, we defined our parameters, and we said MTK build, whatever that does. And for many purposes, you don't need to know what these things are, except that they're kind of like new keywords to the language that Modeling Toolkit is introducing. So @ variables is a very nice way of defining these variables. And notably, one of the things that it does is it makes sure that the name that you happen to give the variable is also a name that the variable itself knows about. So by default, Julia's naming are just for you and me. They're just for the programmers. If I go down to our first construction here, where we have d = 1, this d, the number 1 here doesn't know that it's a number 1, and it doesn't know that it's a named d. That's for me to talk to Julia and talk to the computer and help keep my world straight, but the computer itself doesn't care. It also doesn't know that this is a parameter as opposed to a position, right? Our x's, Julia itself doesn't know how we want to use these. It just knows that there's some data somewhere, and the x's name that we gave it here is, again, just a name that we used for ourselves to name this array. It's nothing inherent about that array even knows that it's been named in the first place. And so this is a little different from other languages, in particular C, if you're familiar with it, where there's explicitly a location for variables. We don't do that. They're just names for these things. But when we talk about models like this, it's nice to know what these names are, because then we can do some symbolic things with them. We can redisplay them using the names that we're using ourselves, and make sure that the name that we're using in our code matches the name that the system itself knows about, and can enable all sorts of really nice introspection on the models that we build. So that's one thing, one very small thing that these macros do, but it's an important one, and it helps keep all of those things together for you. So same thing with component. We're gonna, this is a new keyword that Modeling Toolkit exposes, and we're going to say, hey, let's make a component, and it's going to act like a function, and we'll call it our spring. And all components in Modeling Toolkit need to know what their name is. So you pass in their name, and our spring, it needs to know what its K parameter is here. And so this is, using the component macro to define, hey, this function that we're going to call spring here is going to be used as a modeling component. And then inside here, we can add more things, right? So remember, what we want to do here is, well, remember, our spring, all it has is a parameter, right? So we have parameters, are often abbreviated in Modeling Toolkit as pars, but again, this doesn't really matter. And we say, okay, this is just like the case before. We're going to flag it as a parameter, and it's going to be K, and we're going to grab it from the value we passed. This K equals K looks a little funny, right? It's kind of like a tautology, but what that's doing is it's saying, right, the parameter named K is going to get pulled from the argument that we passed. The thing that's on the right-hand side matches what's here, and that name could be different. But often by convention, we just keep it the same because it looks the same and it is the same. So that's the one parameter that we have, and we keep that separate from the variable, is going to be, right, again, this special variables macro, where we are going to, what do we care about here? What does the spring care about? And we're going to use this common terminology that we have here, where S is our position, V is our velocity, A is our acceleration, and F is our force. And what we want to know is, how stretched is the spring, right? And so this is where using this terminology is helpful, right? We want to know the displacement of our position, right? And so we'll use the language of delta here, to represent displacement from the natural position, not to be confused with the derivative itself. And we have the force that's being applied to the spring, right? So those are the two variables that the spring cares about, right? And the spring equation is just F equals K times this displacement. Now what? Well, that's exactly it, right? We want to have our equations. So we can define our set of equations here to be that answer, right? So we know that our force is going to be equal to the K times our delta S. And since I've defined these up here as parameters and variables, I can just use them down here. The one tricky thing that takes a little getting used to is that when we define equations in Julia, we don't use an equals sign here. An equals sign in Julia means that we're giving a value, a name for you and me to work with, right? So it's saying like, hey, this is going to name this. We don't want to name K times delta X, but we want to say that there's a relationship here. And so Modeling Toolkit uses the tilde, the squiggle, in order to represent that this force is going to must be equal to, or it's like that mathematical equality between the left-hand side and the right-hand side. So that is our force, and then we return, and so this is a function, right? So we, just like our function before, it needs to return something. And what does it return? Well, it returns an ODE system that includes our equations. It includes that t, that time that we grabbed from Modeling Toolkit long ago up above in the system here, and we pass that here, and then we pass our variables, we pass our parameters, and we also want to say that the name is what we gave it in the argument here. We're going to pass that along, so that way the system itself knows what name we're using for it. And then there's this question of, well, how do we know where the endpoints of this spring are, right? How do we attach this spring somewhere? How do we know what this delta S is? How do we find that? And And the answer is, well, we need to define a port, a thing that to connect it to. And this is another kind of component, but it's actually a connector, because we're going to use this to connect components together, and it allows variables from a given component to pass along to another component, which is exactly what we want, right? We want to be able to connect our endpoints of our spring to the endpoints of our damper, and connect those things to our road, and connect, apply a force or a mass to the end of these things, and get ourselves, propagating systems across these things. And so that's what connectors do. We'll call this a mechanical port. And this uses a somewhat similar, way of working. We have this special connector keyword. We name it a mechanical port, and then we have this block of code that's wrapped with a begin and an end, in which we include, the variables that we connect. So what do we connect through a mechanical port? Well, the one perhaps most important one is the force, right? At a mechanical port, the forces must be equal. And actually not quite equal, they need to be opposing. Every Newton's first law, every force must equal all other forces, right? If you push against something, it must push back. So this is, our force that we have. And the force on one side of the port must be, the opposite of the force of the other side. They must cancel out and equal zero, kind of like that equal zero that we did in the toy example above. There's another thing, though, that's happening here, and that is that we are connecting not just the force, but also the position of of these things, right? We're coupling actual physical things together. And so to do that, let's couple them through the velocity component as a nice way of doing that. Now, there's two little optimizations or changes here that I need to do. One is that the velocity and the force are fundamentally very different things, right? Remember what I was just saying about the force, it needs to cancel itself out. You need to have a zero net force across any connection. And if you have a force that is not zero, well, that means that you're going to break something, right? like that port has broken if there's a non-zero force. So we need this force to always be zero, whereas the velocity on both sides of our port needs to be the same, right? So the sign of these things differs. And the way that we flag that in the language of connectors here is by saying that the force is a flow connector. This is just a little bit of a magic flag that we pass here. And this is not real Julia syntax, but rather a syntax of the connector macro itself, where we say this is our variable, and this is how we want this to connect through. We want it to flow through such that everything cancels out. So this is a flow connector, whereas the velocity by default will connect such that they're equal. There's one other thing that I need to do here that can be helpful is let's provide the system with a guess. That can be helpful just for speeding things up, and our velocities will start at a velocity of zero. Same thing with our force. Let's just guess at zero. That's just a nice little thing to do to help ourselves keep track of things. So this gives us our mechanical port. Now we can use that, right? So I've evaluated this, we can use this, and that's exactly what we do in our spring, right? So now not only do we have our parameters, we have our variables, but we also have systems, other systems that can attach to or work with these things. And this is a block here that we can do somewhat similar to variables and parameters, but all we need to do in this case is make sure that these are named components. So just like before, we do a named begin end, and just like I was describing earlier, the names, make sure that the names that we happen to assign to these systems are introspectable by the system itself. And let's call the two sides of our spring flanges, a nice word. So we'll have the flange A being on the one side is going to be the mechanical port, and flange B is going to be our other mechanical port. And this will then allow us to determine what that delta S is, right? Because our delta S is going to be the displacement between our flange A and our flange B. And in fact, remember that the mechanical port is defined in terms of its velocity. And so what we want to define here is that our derivative of our displacement, derivative of that delta S, is going to be equal to the difference in the velocities of our two flanges. So flange A dot velocity minus flange B dot velocity, right? And I'm doing the exact same kind of thing that I did before, where I'm kind of digging into getting a value out of the mechanical port with this dot access. And it knows that that's a velocity term because of how everything works. So that is our two flanges. There's two more things that we need to make sure are constant or held by the spring. So those are our flanges, and we want to make sure that the force going through these flanges is equal to the force of the spring. And it can be a little tricky to get these the signs correct here, but we want the flange on the A side of our spring to be the positive force and the flange of the B side of the spring to be our negative force. And this, you could do it either way, but you have to be careful about then how the subtraction ends up working. Because we're subtracting flange A velocity minus flange B velocity. We want flange A to be the positive and flange B to be the negative. But it's, you can choose either way. In terms of the spring, it doesn't care which side you consider to be the positive force and the negative force, because it could go either way. So that gives us our systems. We need to pass these systems to our ODE system to kind of link it all together. So that's how we do this. This is now our complete spring, where we have parameters, variables, systems to connect the spring to other things, equations that define exactly how that works, and then the ODE system bundles it all together for us into a final wrapped thing. There are 4 what we call positional values here, and then 2 named values. And these named values just are different calling convention of saying, name equals what we named as our name of the spring, and the systems as being these named ports that we pass. So I can define our spring. That was a lot, right? And I took a long time stepping through that because there's a lot going on in this definition. And I think it's helpful to see exactly how we build up each and every single one of these components. I'll go a little bit faster, right? We still have a few more things to define. We have our spring. Now we need to define our damper, but we've done a lot of the hard work, right? We have our mechanical port. So we'll do this exactly the same way. Component, and we'll have a function damper. Same idea. We pass a name, and our parameter that we're passing this time is not our K constant, but D for the damping constant. Same idea. We're just going to mirror the above definition exactly. So we have pars, our parameters, where we begin and end, and we define, and this is just our D. Remember, that's what we passed through. Our vars, we have our variables, begin and end, and we want, now in this case, what does our flange care about? It's a little bit simpler, right? All it cares about is the velocity and the force. We don't need to worry about the displacement in this case. It's a much more straightforward, and this is more common, right? Where you just know, there's a velocity term and a force term. Again, we can do the exact same thing that we did before with our port. We could add a guess here, which can help speed things up a little bit. And we could do that with our variables of our spring as well. I'm not going to go back and do that at this point. let's just keep mirroring our spring. What we want to do is we want to have our systems, are these named, and just like the spring, we have two flanges, right? And actually, I could just copy and paste this, right? Our damper, we'll use the same terminology even, right? Flange A and flange B. That's straightforward. And then our equations are a vector of equations like this. And what do we need here? Well, our velocity is going to come from the difference in velocities of our flanges. That's straightforward. We don't even need a derivative operator there because we're just working in the velocity space here. So flange A velocity minus flange B dot velocity. Our force is going to be represented by, remember, this is just that, go back to our equation, right? It's the velocity times our damper coefficient. So that's going to be our force for just this one component. Again, it makes it really simple. You know that you're doing this correctly. Velocity times displacement, the damper coefficient. And just like the spring, we want to, propagate the forces back out such that, flange A and flange B grab their plus and minus forces appropriately, right? The force needs to propagate through the damper as it does its work. So this is our damper. Oops, I didn't do this right. I missed one last thing, and I think it'll return an error here. Oh no, it doesn't. But if once I started trying to use it, it would give me an error because I need to bundle it all up into that ODE system again, right? And this is going to be exactly the same as what we had before. Just copy and paste it. There we go. So we updated that. Okay, so that's our spring, our damper, and now to make this a little bit more comprehensive than our toy example, let's add a mass to it as well, right? So we have a mass spring damper. What does our mass look like? Well, it's a component. It's a function. It's named mass. You give it a name. We have a mass, and in this case, we're going to have a gravitational constant as well that we can define. I could even give it an initial value because I know pretty much 9.8 meters per second squared or 980, depending upon the units you're using. We can pass that gravitational constant straight through. So what are the parameters? Exactly the same as before. Parameters begin. Except now our parameters of our mass are the m for mass and our g for gravity. Our variables, what are the variables of our mass? Parameters begin. Oops, not variables begin. So what are our variables for the mass? Well, this is where the state vectors, it's just easy enough to name them all, right? We know that the mass has a position, we know that it has a velocity, we know that it has an acceleration, and we know that it has a force. So we name them all as our variables, and we can do exactly what we did before. Let's just guess 0 for all of these, speed things up a little bit in the solution that we end up using. Systems are going to be our named systems. And again, we have a mechanical port here that propagates something that's connected to the mass to the mass itself. And we only have one of these, right? So it's just one flange that the mass is sitting on is going to be our mechanical port, like we had defined before. And now what are our equations for our mass? This is just F equals ma, right? So you can do exactly that. So m times a is proportional to the force, but let's also add in here our gravity term because we're going to be looking just in the vertical direction of a bouncing car. We're not going to worry about any other directions in this case, but we'll add our gravitational term on the right hand side here. Doesn't really matter how you do this. This is all symbolic. And so Julia will happily rearrange them in the most efficient way possible. We need more than just mass equals force times acceleration, though, or force equals mass times acceleration, pardon me. We want to be clear about how all of our variables are named, right? These S's, V's, and A's, they're just names that we're giving them. They're our own conventions. Sure, the thing knows it's named S, but it doesn't really know that an S is position, V is velocity, A is acceleration. Let's define those. So our D of S is going to be velocity, right? Derivative of position is velocity. Derivative of velocity is our acceleration. And we need to grab our forces from our flange, right? So where do we grab those from? Well, our velocity has got to match what the flange gives us, right? It's got to be connected to the spring. If it's not connected, then we've become a catapult instead of a mass on a spring. So flange dot B. And our force is again also connected to flange F. So this gives us our mass spring damper, all of these things together. Oh, whoops, I need to do that final return. And again, this is because it's such a standardized system, I can just copy and paste. And once you start seeing these things over and over and over again, it becomes very easy to start reading them and seeing what's happening and understanding what's going on here. So that's our mass. Now what do we do, right? How do we put these all together into a mass spring damper system, right? We need to connect all three of these things. Each one of them kind of is responsible for what it knows of the world, which is great and awesome for encapsulation, but we want to connect things now. And how do we do that? Well, again, it happens through those flanges, through those mechanical ports that we put as our systems. And what does the combination of all these things, what is that? Well, it's itself a component, right? A mass spring damper is a component. Components are functions like this. And in this case, we'll just know about its name. We'll worry about all the parameters and its definition. And in this case, now we're actually going to do something real here. We're going to take some mass, connect it to a spring, connect it to a damper. And so our parameters here are going to be parameters begin. These are going to be the actual values that we want to use. So let's use 1,000 as our mass. We can set gravity. We can imagine that we're weightless, right? If we wanted to. Our stiffness of our string, our K factor, right? We can set that to be some value. Our damping of our shock, we can set that to be some value. And we can say that we have some initial position of our mass, right? This could be anything. We could have it offset or whatever, it doesn't matter. We'll start at 0 though. Okay, so those are our parameters. Our variables are going to be nothing, right? All our variables are encapsulated in our mass spring damper. I'll finish this and then we'll take questions of the entire system at a whole after we put these things together. How do we define those systems though, right? The mass spring damper needs to know about them. So our systems are going to be this named collection of our damper. It is the damper, you just call it, right? And we pass in, this is why we gave those arguments in our functions as we define them, because we wanted to pass in, D is our damping parameter. Our body is going to be the mass, where we're going to pass in our M is the mass parameter, G is our gravity parameter, right? All of these things we can do. Our spring is going to be our spring function. You'll note that I'm using capital S's, for the type or the function itself, and lowercase. That's meaningful. Those are two different things. The lowercase spring is an instance of the spring model. The capital S is the model itself, and this is an instance of it. The spring, again, we pass in our stiffness as that K spring constant. And now we want the entire system to have inputs and outputs, right? We want our mass spring damper to be able to, in this case, for a road, we want the bottom side to be able to connect to the road. The mass should be observable, right? We want to know what that mass is. So we can do these again as mechanical ports. So these are our inputs and outputs of the combined system, mechanical port. So M will be our port on the mass side. SD is going to be the port on the spring damper side. So those are our systems. Now, what do our equations look like, right? So we're just following exactly the same idioms that we used for our other components, but in this case, it's different, right? We don't have variables. There's nothing that this mass spring damper collection really cares about itself beyond the parameters that it's passing into the components of that it encapsulates. So what is in these equations? Well, what's there are the connections. We can say modeling toolkit.connect our damper with our spring with our mass, right? Our body is what we're calling it. But how are we connecting these things, right? We have our damper and our spring and our body. What are we actually connecting here? Well, we need to explicitly say we're connecting the mechanical ports, right? And we're going to connect our flange A of our damper and our flange A of our spring with the body of our the mass, right? Just the flange of the body. So that says we're saying the A side of the damper and the spring get connected to our body. What about the B side, right? Well, the modeling toolkit.connect, we want to connect the port SD, right? This mechanical port here for our mechanics of this. We're going to connect that to the spring, the flange B side of the spring, and the flange B side of the damper. Doesn't matter which order you put these in. Flange B, like that. Okay, great. And then we have our initial is so following this thing, right? We have our ODE system here, right? We would want to just return the ODE system. There's one thing that's missing, though, in the case of this system as a whole, and that's the initialization, right? We need to say where all of these things start. And where do we start? Well, we want to say where that body starts, where that mass on the end of the spring starts. So we can set an initialization equations are going to be our body.s is going to be that initial position that I defined as a parameter. And our body.velocity, let's set that as 0. Our body.acceleration, let's set that to be 0. And then we need to pass in our initialization equations to the system itself. And that is done like that. So now we have a complete mass spring damper, and we can actually model this. I'll get to that. I know we had some raised hands and some questions. I'll pause just for a moment. I know that we're also at the top of the hour. I'm planning on going till 2:30 here. So I hope that you're able to join me through that. We'll see exactly, get to the end of this story before that time. Okay, so let's model this mass spring damper, right? We can build it as a model. And again, we'll use that special MTK build to say our mass spring damper is mass spring damper, like that. What this MTK build does is it goes through, defines all of the equations, figures out what's happening. It simplifies them, does some structural simplifications, tries to make it as sensible of a system to solve. Let's see, what did I miss here? I missed. Probably missed a subtraction somewhere. Shoot. see, I've also lost my connection with my notebook. Try to get back to it here. Okay, great. So we have our MTK build. And yeah, this is the challenge with doing this in a live system here. So let's see if I can figure out what I missed in terms of this. And I think that all looks right. We have our, just comparing against my cheat sheet here. Yes, is velocity. Yep. Okay, great. That looks okay. Our flange velocities are, yep, that looks okay. Okay, well, I'll have to pause on that. We'll come back to that, see if I can come to a conclusion. But the answer here is, if I just model this mass spring damper in isolation, what ends up happening is that we yeah, let's see. I don't know. What happens is nothing happens, right? We're not applying any forces to the system. We're not doing anything. And so even if I hadn't gotten this, it wouldn't be very interesting because you don't get anywhere. So we'll come back to this, see if I can solve that later. Let's build a road. Let's make a road that we can drive our car on. And to do that, we need a few more utilities here. The one most important one is that we want to have a numeric, like an equation governing like what our road is going to do, right? And so we can create a system that kind of defines its equation based on that. And I'm just going to copy paste what I have here just to make sure that I don't mess it up and kind of move along a little bit here. But this is one way of doing a system where we have a like an algebraic way of defining what some value is going to be in our system, in our component-based modeling system. What this is going to do here is, we have a very simple bump equation, and we're just going to, every 10 seconds, we're going to loop and bump and give ourselves some value that we can look at what happens to our mass spring damper, assuming that I'm able to get that working, but we'll see what happens here. So we have our ODE system. You'll notice, though, that there's one system here that we've not seen yet, and that's this real output. And this is just, again, kind of like that mechanical port connector, but it's this kind of phony system where what we want to do here is have we want to have some way of grabbing some real number as input and output. And this means that there's not like forces or other things. It's just a value that we want to propagate and use as an input to our system, right? So we have a real input and a real output. The output of this numerics here, this kind of funny way of creating a bump in the road, is going to be used as an output from our road. And we'll use that as an input to another connector here, or rather a component here that we will grab and put in. And that's going to be our position, right? So it's going to be kind of the position of the road as that road data varies. And all it's doing, all that's happening here, is it's connecting that positional signal from that algebra, that very simple cosine function here, carefully placed so that way it can look like a bump that we can introspect. What that's doing is it is looking at the connecting that to the velocity of a mechanical port that then we can connect to our mass spring damper. So this is just a very simple way of doing a numerics sort of thing and connecting it as a component to our system. So let's define these, and then let's take the 2 questions that we have. All right, those who have I see. Oh, I'm so sorry. I wasn't scrolling down on the Q&A, so I missed this. Yes. Okay. So there are a number of questions that we've had that I wasn't scrolling down and wasn't seeing. My apologies. So I'll pause here and take these things. So question a few minutes ago, what is the rule for what goes on the left of that tilde and what goes on the right-hand side? That is, it doesn't matter. These are symbolic equations, and you can put it in either way. The convention is, derivatives are on the left, but you can do it either way. There's another question about ways that we can draw these systems, and yes, this is definitely where we're going. The real value of being able to do this component-based modeling is that then you can start abstracting away from the components themselves. So you can define components. You can start imagining these as black boxes or block diagrams, right? And they have ports, and you can start imagining connecting those lines. And that's exactly where we're going with JuliaSim. Today's webinar is just about the open source modeling toolkit, but encourage you to get in touch with us about JuliaSim, which is work towards those things of being able to use these components as block diagrams and connecting them and drawing it together. So those are the 2 questions that we had. I guess another question here is in terms of how we can specify the initial size of the spring as a parameter of the spring. Well, in that one, we have our when we defined our spring, right? We have our parameters here and our delta S, and that's going to just be the initial values of the flange displacements, and the S's there. I don't have the system set up to that, but you can definitely have a initial value of delta S as well as the initial value of the spring itself. So that's just passed as an initial value. For the spring, it doesn't matter because it's just all in terms of displacement. I guess to do a more rigorous modeling exercise, you would want to make sure that you have that displacement there. But that actual length, we're assuming it's an ideal spring, which of course in this real world that's not the case. Okay, so that gives us our road, and now let's go on and create a system where we can put this all together. Let's see, I think I have a cell here that's not commented out. There we go. Okay. So what we want to do here is, connect now our road to our mass spring damper. How do we go about doing that? Well, in this case, what we're going to do here is we're going to create, any guesses? What are we going to create to put this all together to connect our road with our mass spring damper? It's going to be a component, right? So our component is going to be, again, function, wheel, system. This is hopefully getting tiresome, right? Yeah, you're hopefully seeing the repetitivity, seeing and understanding how and why I'm doing this. And just like the mass spring damper system, the wheel system that knows about the road and the mass spring damper that's riding on top of the road doesn't have any parameters, doesn't have any variables, doesn't need to have any of these things, and just has the systems, right? Where we have our named systems of the mass spring damper is going to be our wheel. Approximation of a wheel is going to be the mass spring damper. Our road data is going to come from that road input. and we're going to connect that to our road as a position input that we can then pass to the mass spring damper. So those are the three components that we'll have in this, systems model. Our equations, again, are going to be pretty straightforward, right? They're just going to be modeling toolkit connect our road, our position of our road with the road data output. We're going to also connect modeling toolkit.connect our road flange with the wheel port of the spring damper, right? And then the mass is going to be wobbling around on top of that. And we return an ODE system of our equations, our time, our vars, our pars, and passing in the name of our system as well as the systems themselves. That gives us our wheel system. Now let's see if I did this in a way that if this was where the problem was or if it was somewhere else. But let's try this. Let's build our wheel system. MTK build our wheel system. Wheel system like that. Yep, I was afraid of that. Okay, so we'll have to figure out where I'm missing. I think I'm missing some. So what this error is saying that I'm trying to subtract an entire system from a symbolic value, and what's probably missing here is I'm probably missing a dot f somewhere, or digging into the actual value in order to get the forces. So I think that's exactly what I'm missing. Let's see if I can find that quickly, because this is the fun part of actually being able to grab this. And I think it's here, right? The port, we want to connect the port. Is that where it is? Nope, that's not it. Right. Oh, dot flange, maybe? Oh. Yeah, that's how it is in my notes here. I don't know, David, have you managed to figure out where I flubbed in the copy paste of the notebooks here? Like my re-implementation, it's a dangerous thing doing live coding. While I look through this, please, feel free to type your questions. I'm happy to answer any questions that come up. One that is very, very notable here is, this debugging is a little tricky, right? In particular, you can see that. Let's go back to our, rerun this here. Oops, rerun this and then. And that, right? So you can see that no method matching is a very common thing that happens. And it happened while we were doing the structural simplify of our systems of equations. And so there's some equation here where I'm passing an entire ODE system instead of a symbol. And that's precisely where this is happening. So the errors that you do see, we are always striving to improve these, and it would be really nice to be able to debug this a little bit more closely. Doing it live is tricky. Yeah, go ahead, David.
In the mass spring damper function where for your equations, the first connect command, does it need to have the port M in there somewhere?
Yes, it does. You're right. I think that's it. In my notes, that's there, and it's on a different line and then hidden behind the chat window. So that was definitely one problem. Doesn't seem to have been the problem though. Shucks. Good catch. We're getting closer. That is the right idea though, right? Like we were missing that connection on the mass side of things. We're connecting the spring the body and our mass port to that. So that way we can, it's kind of like attaching a scope for those of you coming from other systems, right? This port allows us to introspect that in a nice, easy way. So that was one thing that I got wrong in rewriting this. Thank you. Let's see if I can find. So then this one looks, I guess what I could do here, it's going to be in one of these mass spring or damper. I can copy and paste these in and reevaluate them and see what happens from my notes. These should be exactly the same. But that, so in either one of those two things was the problem. We solved it here. I guess I could look and see. Doesn't look like it was in this one. That looks exactly the same. Yeah, I'm not sure. Well, it's okay. We the final version will have the correct answer here. I'm sure I just typoed something, but you can see that our mass spring damper system knows its systems of equations, which is what we should have seen 20 minutes ago. When we connected our road now to it, we can see that we have our wheel system. It has all of these equations to it as well. And now we can go in and solve this, right? So what we want to do, how do we solve this system? The same way we solve all ODE systems, right? It's an ODE problem with our wheel system as the equations. We don't need to pass in any initial values. We'll just use the ones that we defined in the system itself. We'll do it from 0 to 20 seconds. And what we want to do here is we want to pass in some initialization equations that say how we're going to solve this. So when you define an ODE problem like this, you can pass in some initialization, and we'll do that. What we want to initialize is just kind of like what we did with the mass spring damper system. Those initialization equations are going to be going to set our wheel sys dot our body dot s is going to be 0.5. Our wheel sys dot body dot v is going to be 0.0. Oops, and you wanted to use the tildes here for this. Wheel sys dot body. And effectively what this is doing, to answer the question from before, right? This is effectively setting that initial value of the spring distance, right? Our body is going to be 0.5 position offset from everything else. And that's going to be that difference. That's going to be our initial value there. So that is where that goes. Let's see, what did I do wrong here? Oh, it's wheel sys dot wheel dot body. Because it's the location of that mass spring damper that's inside of the wheel system. So you can kind of dig into the entire system, get your wheel, the system of the wheel and the road, and then grab the wheel and the location of the mass on that wheel, and then the position and the velocity and the acceleration. So it's a deeply nested problem, but that's, it's nice to be able to know exactly what component you're working with, and it's all named here. So then we can solve this ODE problem here with those initial values. Oh, and I had specified a DT max here in solving this. That might be helpful in speeding this up just a little bit. We'll let that go. And then what you want to do is, right, we'll name this our solution, and we'll want to plot that solution. You can just plot it as plot sol. You're going to also do a little bit of a fancier plotting, by digging into these things. And in the interest of time here, I'll grab these like this. So plot these, and again, right, like you dig into the wheel system, right, and you can find a particular indice to plot. So here's we have our solution. Let's name that.
Matt, one more try. One more thing when you get a chance. In your function definition for your spring,
Yeah.
inside of the equations, does oh no, it's there. Never mind. I thought the
Yeah,
flange A
but
was
it's
missing.
working now. So somehow when I copy pasted from my notes, I overwrote the typo that I had. So this is
Oh,
working
okay. You were
exactly
missing
as I
the
expect it to
F
be.
after the flange A, which Justin Wilmer actually pointed out, though. But
Ah,
yeah.
that's what it was. Oh my
Yeah.
goodness, I should have been looking at the chat. Thank you so much, and good catch, everyone. So yes, we've come to the end of our road here, as it is to say, where you can plot the entire system, and by default it grabs, you know, the simplified things that it's solved for, which may not be the variables of interest, right? So when I just plot the solution, these are the things that structural simplify kept as the independent variables. Not all variables are independent, and it just kind of, you know, which ones it ends up using there can sometimes be a little random. So that's where it's nice to, you know, explicitly say that you have a plot here, and oops, I called this sol in the actual thing. Where you can explicitly say, let's just look at that bump in the road as blue, and the wheel body, the mass and the wheel itself as orange, and you can see how the mass and spring damper. So then the next question, where this leads you, of course, is how do you optimize this, right? And where do you go from here? And perhaps the most fun part about this, once you have the basic definitions down, becomes even easier to connect more and more things, right? So that's where we can take our system that we had, right? We just had one mass spring damper here, but you can extend this much farther, right? So you could have the wheel, the representation of the wheel as a thing. You can have the representation of the car mass spring damper as another mass spring damper. You can have the seat of the driver as another mass spring damper, right? Each one of these are its own systems. Each one of these I could, you know, define parameters for, pass independently. You know, you can set them up, and all you need to do is connect them, right? So what do we need to do? We just need to add a few more connect statements here. Toolkit.connect, and we connect our wheel.port SD or port M to the, you know, car.port SD, right? And we connect our car.port mass to the seat.port SD, right? And so on and so forth. And so this is, you know, just drawing those lines between the boxes. And it's really that straightforward to do. I'm not going to run this here in the interest of time. I know we're over time, but I want to thank everyone for your interest. Thank you for flagging those problems that I had. I wish I would have been reading the chat a little bit more closely. And I'll stick around a few extra minutes here to answer any questions that folks have. Thank you so much for your time, and thanks for being a part of this. We're really excited about where Modeling Toolkit and is going with component-based modeling, and in particular as we build it out and further extend its capabilities through Julia Sim. Please don't hesitate to get in touch with us about those things. And like I said at the beginning, I'll have this cleaned up version of the notebook put together and exported publicly on JuliaHub, so you can see exactly what we were doing and come back to this. So thank you, everyone. At this point, I'll jump over to the chat and look at the Q&A and try to see, you know, which things that we were missing. If I hadn't answered any things. A notable question about how does this compare against other solutions? I think the biggest difference, kind of at a abstract level, is that this is what's called acausal modeling as a large framework. And what that means is that you don't actually have to track time as a thing in the system. So in causal modeling systems, one of the main things that's happening there is you have a time, and you're explicitly taking the value of the previous time step and kind of connecting it back around to the next input, right? You have that loop around to kind of feed things forward. That's causal modeling. In acausal modeling, we don't really care about the time-based, what the time evolution of the system is. What we care about are those core fundamental equations, right? So F equals ma. We care about the F equals k times x, or the force equals the damping coefficient times the derivative of x. All of those things that's what we care about in an acausal modeling framework, and so that we've found to be a much more extensible and composable mechanism for modeling, and that's going to be one of the biggest differences that you'll see in evaluating. There are other solutions out there that are similarly acausal, and there are other solutions that are the causal modeling, where you're working more in the time domain than the actual physics of the system. A question on package management on JuliaHub. Yes, it can take a while, especially the first time that you do this. So one of the ongoing work items within Julia itself is towards improving time to first plot, and that has increased dramatically and done so in really wonderful fashion, but it's done so at the expense of the install time. So when you run, or when you install Julia for the first time, it needs, and importantly, install all the packages that you need to use the first time. It needs to go out and do what we call pre-compilation of those packages. It's really just compilation these days. It compiles the packages for you and does a lot of the work ahead of time, but it's not quite far enough ahead of time yet, right? You're still downloading the source code, and it still needs to compile them that very first install time. That's what's happening on JuliaHub and in Pluto when you add packages the first time. So if you've never been on JuliaHub before and you add packages, and particularly different versions of packages than you've ever used before, then you will see, it takes a while to do that. When you come back to JuliaHub and come back, importantly, to the same notebook the second time, the package management should be less than a few seconds. It's very quick, and then the time to first plot is similarly less than a few seconds. We're still working on that time to install problem, but the problem is incrementally getting better, and we're excited about a lot of those improvements. Looking back through other questions here. A really wonderful question that leads perfectly into what we'll be doing during our next webinar. I believe that's scheduled in a month from now, is how do we add a controller into the system? And that is exactly where this goes, right? And we actually intentionally do this through a suspension model, because it's very straightforward to think about. Well, you can have an active suspension with a PID controller. What would that look like? And it's done exactly the same way with a component. And so I hope you'll be able to join us at our next webinar, where we'll extend this system and look further into control design of within Modeling Toolkit. And finally, one last question here about running Julia locally. Yes, of course, you can run this locally. There's the only thing that JuliaHub is providing in this case is the notebook viewer and system. It's also just a really nice way of running Pluto if you've not installed it. But if you have Julia installed and Pluto installed on your local environments, by all means, you can download this notebook and work with it. So with that, I want to once again thank everyone for your time. And I know I went 8 minutes over here, but I hope that this has been a helpful session. And I happy modeling. I hope that you've learned a little bit more about component-based modeling, in particular, how you can combine and build out component-based modeling from zero is really the point that we started from here, right? And that's where I got myself in trouble, where in the spring system here, what I was missing was the dot Fs, I believe, in the flanges here, that we ended up missing. So, doing this by hand it can be a little tricky and can be a little daunting. One of the things that can help, though, is each one of these systems is self-contained, and perhaps the simpler thing for me to have done in the live debugging session that ensued would have been just to look and see, can I build the spring itself? Can I build the damper itself, and narrow in on exactly where that problem was? But live debugging is always hard and always makes things interesting. So thank you again. We'll bring this session to a close.
Thank you, Matt. And we will share the record version of this workshop with everyone over an email. And our next workshop is on September 25th, and I'll send the link to that as well. And hope to see everyone at that webinar, at that workshop as well. Right. And meanwhile, if you have any questions, do write to us and we'll respond to you as early as possible.
Great. Thanks, everyone.
Thank you, everyone. Thank you, Matt. Have a great day.